Okay, so now I'm ready to say the third interpretation of the propagation law for the gravitational wave field. Third interpretation is that, and it's an interpretation which is obviously equivalent to the previous two, if you think about it in a local Lorentz frame. It is that because Hj goes as 1 over the radius of curvature of the phase fronts in a local Lorentz frame, correspondingly, Hj squared times the cross-sectional area of the bundle of gravitons that are moving along that direction. They're sitting in the surface of constant phase and moving along the orthogonal direction. Hj squared times the cross-sectional area is a constant along a ray. So you pick an arbitrary ray, which means an arbitrary graviton. You pick a bunch of other gravitons, a small bundle of rays that lie in the same, in the surface of constant phase alongside that one graviton. And you just follow how the cross-sectional area of this bundle of gravitons behaves. And the statement is that Hj squared times that cross-sectional area will be a constant along the ray. Equally true for electromagnetic waves and photons, and for gravitational waves and gravitons, and for neutrinos, or any other kind of a particle that's moving along at the speed of light and is conserved. It's just they're all equivalent to the law of conservation of quanta. Okay, are there any questions about that? So let me quickly do an example of this. I'm going to give you some reading about this example, which says more or less the same thing as I'll say here in class, but I really want to emphasize it. It's important. But I'm not going to work through the mathematics. I'm just going to say what happens when you do the analysis using these tools. So I want to consider a plane fronted gravitational waves, propagating through and past the sun. So I have the sun here, and here are the in a particular Lorentz reference frame, or almost Lorentz reference frame, it's as Lorentz as I can do, given that the sun is producing a little bit of space-time curvature. The waves are coming in with plane fronts, and the rays drawn spatially look like that. So, and this is a stationary situation in the sense that I just have a steady train of waves coming along. Nothing is changing in time, and I just have a pattern where these waves are going to be gravitationally focused by the sun, in fact. So I can talk about everything just in terms of a spatial diagram instead of a space-time diagram, since there's nothing changing in this picture over time. Though, of course, any given graviton moves along some spatial trace, some spatial path in this spatial diagram. But the overall picture is unchanging. So partial derivative of anything with respect to time at fixed location in space is 0. So the temporal part of a space-time diagram is pretty trivial. I'm just going to draw the spatial part. Now, a ray then drawn spatially in this diagram, as it passes the sun, one can show that because it's a null geodesic, it gets deflected. It gets deflected through an angle that is 4 times the mass of the sun divided by, let me call it b, where b is the impact parameter. So rays up here are deflected only a little bit. A ray down here is deflected more strongly. And similarly, rays out here are deflected fairly weakly. And these guys come to a focus somewhere out near the orbit of Pluto. And these two guys may come to a focus somewhere out near the orbit of Neptune. And the earliest focus that you can imagine would be for rays that come in not right at the surface of the sun, because the sun has rather low density near its surface. It actually is quite centrally condensed. Most of the mass is down near the center. So you go down near the center, and there's a sort of a homogeneous core near the center, and then the density starts falling off rather sharply. So you go down in here, here's the homogeneous core, say, down here, and I'll ignore the rest of the sun for simplicity and just talk about that homogeneous core. And this will be its radius, and it has some mass for that homogeneous core. And the strongest deflection and the shortest focus is going to be down here. And so this is, the sun acts as a lens, but it's not a very good lens. But the strongest focusing is going to be down in here, and there'll be weaker focusing out there. So I want to look here where the strongest focusing is. And so you can ask, what's this focal length out to that focus? Well, given the fact that this impact parameter is r, and this angle of deflection is 4m over r, you can easily see that this focal length, f, to the focus, this focal length f is just equal to m divided by 4m over r. I'm sorry, it's equal to r divided by 4m over r. It comes in with this impact parameter r, and then it goes down at an angle 4m over r. And so you have to travel a distance r divided by 4m over r to get to the focal point. Now, the laws of geometric optics say that in order to compute the gravitational wave field, h plus, say, you look at the cross-sectional area of a bundle of rays. So we'll take this bundle of rays here. It has some cross-sectional area, A naught, out here. And you look at what that cross-sectional area is down here. Let's call that A naught initial. IN for initial. When we look at the cross-sectional area down there, I'll just call it A naught down there. And the statement is that H plus squared times A naught is equal to H plus initial squared times A initial. Or so this is H plus initial out here. Or H plus then over H plus initial, the amount by which the amplitude has gone up, is just the square root of A in over A. And so as the cross-sectional area gets smaller and smaller and smaller, this is just the 1 over r statement, isn't it? It's just the 1 over r statement for how things behave. As the cross-sectional area gets smaller and smaller and smaller, the amplitude goes up larger and larger, and at the focal point, the amplitude goes to infinity according to geometric optics. So a very simple calculation, actually, to see what happens. A very simple way to see how the amplitude of the gravitational waves is going to change due to gravitational lensing. And this kind of an argument is basically what underlies the theory of gravitational lensing, which is so important in modern observational astronomy optically. It's the same thing. However, there's a complication. And that is that if these waves really come to a focus down here, when they get down in here, the amplitude may be changing on the same length scale as a wavelength, and the geometric optics is going to break down. And so you have to be aware that when you come into a caustic or a focus, you will always have finite wavelength effects, which we call diffraction. You've all studied diffraction in elementary optics courses. And so we will have diffraction here as well.
How far out is that nearest focus?
So that nearest focus is, since that's Pluto and this is Neptune, obviously this is Uranus. So it's about 20 astronomical units, which is, Uranus is at about 19 astronomical units. So it's very close to the orbit of Uranus. So in fact, there were proposals some years ago to put gravitational wave detectors in space out near Uranus in order to see this huge amplification for gravitational waves that go through the sun. And then people realize you've got to worry about diffraction. Okay. Now, diffraction is an issue that has nothing to do with polarization. And after all, polarization is behaving the same way here anyway as in electromagnetic theory. It's just being parallel propagated. Diffraction is a common phenomenon for any wave propagation. And so you can use the elementary arguments that you would use for diffraction for electromagnetic waves, or for sound waves, or for seismic waves. And those arguments tell you, when you go through the arguments, and that's sketched out very briefly in the reading that I will be giving you. Those arguments tell you that I want to say this very briefly, so let me. They tell you that if the reduced wavelength of the waves is less than or of order, is greater than or of order 4m, then the diffraction destroys completely the focusing, and you get no significant focusing. And so I leave it to you to do the reading and to think about it to see that that's the case. If you have reduced wavelength that is small compared to 4m, then diffraction permits some amount of focusing, but what happens is that these rays get down to a certain size and diffraction effects become important, and the size ceases to decrease, and they sort of reach a minimum size and then start to increase again, going back through the other side. So you look at the size of that minimum cross-sectional area to see what is the maximum possible amplification you can get. And the statement is that H plus or H plus N, the maximum you can get, is just equal to 4m over lambda bar. So if you have a reduced wavelength very small times compared to 4m, and remember the mass of the sun is about 1.5 kilometers in geometrized units. So 4 times the mass of the sun is about 6 kilometers. But we're really talking about the core of the sun, so we're really dealing with something more like 3 kilometers or so. So it says that, what it says is that this is of order 3 kilometers divided by lambda bar.
It's a beam waste.
It's a beam waste. So for people who know about optics with Gaussian beams, it's the beam waste. So the beam waste, the smallest beam waste you can get, given that the focal length is the distance between the sun and Uranus, and given the size of the lens, the smallest beam waste that you can get is about 3 kilometers. In order of magnitude, you can go through the numbers. This says that if the gravitational wave frequency is higher than about 10,000 hertz, you get some significant focusing. But if it's less than 10,000 hertz, you don't get any significant focusing. Now, the gravitational wave band, in which we have interesting sources, at least we think, is at frequencies that are a few thousand hertz on down.
Shouldn't I just be able to stick a bar on the table and look at it change length
Pardon?
At a megahertz? And
yeah, so I mean, if you have gravitational wave sources at a megahertz, this is a great idea. And there could be gravitational waves at a megahertz produced in string cosmologies.
you wouldn't have to build a detector to see that. You just look at the ground.
At the amplitudes that are plausible for gravitational waves at a megahertz, it's exceedingly difficult technically to do anything, and nobody has devised a plausible gravitational wave detector at a megahertz, a really good gravitational wave detector at a megahertz. But at a megahertz, you can gain by putting your detector out at Neptune. But down in the usual gravitational wave band, where most of the action is, down around 100 hertz or a kilohertz or 10 hertz, there's no significant focusing at all because of diffraction effects.
Wasn't there actually some attempt in the 60s to detect waves using metal bars?
There has been a lot of work with bar detectors, and there continues to be work with bar detectors. But they work at decent frequencies around 1,000 hertz. And when you start getting up, at least compared to wave strengths for plausible sources, when you get up to 10,000 hertz, the technology goes bad because the waves are expected to be so weak. And we'll return to this later. So this example does two things for you. First of all, it illustrates in a simple case gravitational lensing of gravitational waves and the fact that it's the same story as for electromagnetic waves. But second, it warns you that if you're seeing a lot of lensing in a geometric optics analysis, you better check to be sure that finite wavelength effects are not coming into play, and you better worry about diffraction in the same way as you would electromagnetically. Okay. And that's where the people who actually worked quite seriously on conceptual designs for gravity wave detectors out at Uranus went wrong. They didn't check this, at least not as soon as they should have, back in the, I guess it was in the late 70s, early 80s. Okay. Any questions? Then in the remaining time, I want to derive my statements about the number flux of gravitons, and I'm going to do it by discussing the stress energy tensor for gravitational waves. And I want to begin with some simple arguments about the nature of energy and momentum of gravitational waves that tell us immediately that there's something a little bit subtle about this. So let's just ask dimensionally, what would we expect would be the formula for the gravitational wave energy density? So the energy density, dE, the three-dimensional volume for the gravitational waves, it has dimensionality of, say, ergs per centimeter cubed. But ergs, since the speed of light is equal to unity in our units, this is the same thing as grams per centimeter cubed. But since g is equal to unity in our units, grams and centimeters have the same dimensions. And so this is centimeters per centimeter cubed. So the dimensions are 1 over centimeters squared, or 1 over seconds squared, if you wish. Okay. So that's the dimensions of energy density. And that's the dimensions of the stress energy tensor. Now we know that this energy density for gravitational waves, it surely ought to go like the square of the amplitude of the gravitational waves. Okay. And let's put hj squared, where j could be plus or cross. But that doesn't have the right dimensions. To get the right dimensions, I had better differentiate this once with respect to time. Then I have dimensions of 1 over seconds squared. And so we expect then, on dimensional grounds, that the energy density must look something like the first time derivative of the gravitational wave field squared. Or equivalently, since we want to talk about the stress energy tensor for the gravitational waves, and since that's a second-rank tensor, what we would expect is that this should look like hj comma mu hj comma nu. Remember, commas, slashes, semicolons, they're all the same for a scalar. Well, let me put on a slash just so we emphasize we're in curved space-time. We expect it should look something like that. where J is plus or cross, and you would have contributions from the plus and contributions from the cross. So for the whole thing, let's just write it as H plus slash mu, H plus slash nu, plus H cross slash mu, H cross slash nu. Now, I have done something here I don't want to go to plus and cross yet for the particular argument I was going to make. And so let me do it in terms of the metric perturbation. So H, it has two indices, and then I would have, say, a mu and an H with two indices and a nu. So it should look something like that, and ultimately it should have the kind of a form I just wrote down. But if I want to write it in terms of the metric perturbation, it will look something like this. Now, let me remind you that if we go to a local Lorentz frame, in a local Lorentz frame, the metric perturbation is constant. The first derivative vanishes. Another way to say this is this looks like a product of two connection coefficients, because you take an H and take one derivative, you've got a connection coefficient, roughly speaking. In a local Lorentz frame, the connection coefficients vanish. And so that's a warning that if we get a formal expression for the stress energy tensor in terms of the metric or metric perturbations, we will have an expression that has the property that I can make it go to zero at any location in space-time I want by going to a local Lorentz frame. And what that must mean is that gravitational wave energy is not localizable. It's not definable locally, because I can go to any location I wish, introduce a local Lorentz frame, and any expression that has the desired form is just going to go to zero. So there are more sophisticated ways to discover this, but the bottom line is, from many different arguments, you conclude that gravitational wave energy is not localizable. And therefore, somehow the correct formula must look like T mu nu gravitational wave is this expression that I gave you before, and you must somehow average over a wavelength of the gravitational waves. There's no other way to do it. If it's not localizable, but surely it must be localizable to within a wavelength, because this wavelength looks like that wavelength, looks like that wavelength. The issue must be you can't say whether the energy is in the trough of the wave or the crest of the wave or on the steep sides of the wave. But you must at least be able to say where it is to within about a wavelength. And so this bracket means average over a wavelength of the gravitational waves, just like I used that bracket when I introduced the geometric optics limit when I defined gravitational waves in terms of a two-length scale expansion. And similarly, then, the bottom line must be that T mu nu gravitational waves in terms of H plus and H cross must look like H plus slash mu, H plus slash nu, plus H cross slash mu, H cross slash nu, something like that. And so that's what we expect must be the case from these simple arguments. And there is a very sophisticated way, a beautiful way, to in fact derive quite quickly conceptually, and the algebra is a little messy, to derive the precise expression for the gravitational wave stress energy tensor. And the argument goes like this. You look at the Einstein field equations in vacuum, G mu nu equals 0, and you average them over a wavelength or a few wavelengths. We have also gone in and we have defined the metric in coordinates that are as smooth as possible. So the only ripples are on the wavelength, on length scales of the waves, and then on length scales of the huge background space-time curvature. And in that kind of a steady coordinate system, as we sometimes call it, the average of G mu nu is what we call the background, and H mu nu is the metric perturbation associated with the waves. If I feed this expression into the expression for the g's, and I remind you that the g's mu nu looks like a product of connection coefficients, basically. It's terms like that. What we will get out is that G mu nu is G mu nu background, where this is computed, it's the piece computed from the background metric. But there will also be terms that are linear in the metric perturbation, and there will be terms that are quadratic in the metric perturbation. And there will be higher order terms. Now, of course, the metric perturbation is very small numerically. But when I do my averaging, this guy is already smooth on the scale of a wavelength. He's constructed from the background metric. This guy, being linear in something that oscillates on a wavelength, the averaging gives 0. And I will have, however, something that is an average of something that is the square of an h. And this piece I'm going to call G2 mu nu average. It's the piece of G that is quadratic in H. It's quadratic in the metric perturbation. So if you just go through all the algebra to compute the Einstein tensor, you'll wind up with this piece and that piece. And what defines this piece is it's the piece that is quadratic in H. And we throw away anything at higher order. Remember, h is like 10 to the minus 21, so the next cubic term is a lot smaller than the quadratic term. That means that the Einstein field equations can be written as G background, the Einstein tensor created by the background metric, by the usual method, is equal to minus the average of this second order G, which is quadratic in the metric perturbation. And I'm going to put the minus sign inside of the averaging. I'm now going to multiply by 8 pi and divide by 8 pi. And I'm now going to define this to be the gravitational wave stress energy tensor. It's a definition. Okay?
Okay, so that's not a tensor field.
It's a tensor. It's a true tensor in the background space-time. It's a tensor field. It's constructed from the gravitational wave fields. These H's in here are gravitational wave, or the metric perturbation. It's constructed from the metric perturbation, and it's second order in the metric perturbation.
You don't have a value at each point in space-time.
Yeah, you have a value at each point in space-time, but because of this averaging, it's smooth on the scales of a wavelength of the gravitational wave, but it will vary on longer length scales. The averaging was crucial in even doing this mathematics. Okay. So it is a field, but it's a field that varies slowly, very slowly. It varies on the scale of the background, actually, or on the scale that the amplitude of the gravitational waves may vary, but not on the scale of the wavelength of the gravitational waves because of the averaging which was used in the definition. Now, it's a very important fact that G background mu nu slash nu is equal to 0 as a mathematical identity. This is the contracted Bianchi identities. And this implies then, by virtue of this way of writing the Einstein equations, it implies as a consequence that T gravitational wave mu nu slash nu is equal to 0. That in vacuum, this is all done in vacuum, the energy and momentum of gravitational waves are conserved. So it's a very quick. Let me say this is all due, and the deep full details as well as the concepts are due primarily to Richard Isaacson, the brilliant relativity theorist, who soon after he did this work took on the difficult job of being the program director for gravitational physics at NSF, and has been a much better program director than any other program director I've ever seen at any agency. And part of the reason is that he's a superb scientist. And he laid the foundations for our understanding of gravitational wave energy. He retired about 5 days ago and is now curating an exhibit of Persian carpets at the Smithsonian. Anyway, so when you go through all of this mathematics, you find, as a bottom line, that T mu nu, gravitational wave, is equal, in fact, to 1 over 16 pi times h plus mu, h plus nu, plus h cross mu, h cross nu. So, which has just precisely the form that I argued it ought to have, and we find out the numerical coefficient. But it does involve this averaging also that I argued that we ought to have. And it's worth also noticing then that the constant that let me look at the J polarization. That T then let me put the indices up. Mu nu for the J polarization is 1 over 16 pi times. If I do the averaging outside, 1 over 16 pi times hj, let me back up. In the geometric optics approximation, let me just say it. If you apply the geometric optics to this, then when you differentiate, that just gives you a wave vector. From the differentiation. And so it turns out that when you apply geometric optics to this, you get that T mu nu, gravitational wave, is 1 over 16 pi, the average of h plus squared plus h cross squared. I'm assuming that these are monochromatic waves, times k, let me put the indices up, k mu, k nu. If I now note that k nu is the formal momentum of a graviton divided by h bar, I can rewrite this as 1 over 16 pi times Planck's reduced constant times h plus squared plus h cross squared k mu p mu, which is just the form that I had down here. And you see that, in fact, if you think about it, this is the number of flux vector for the gravitons. That's the momentum of a single graviton. P mu. Pardon? Nu. So a single graviton carries the form momentum P nu. And if I multiply the form momentum of a single graviton by the number of flux vector of gravitons, if you think about it, you get the energy momentum tensor. You multiply, for example, the energy of a graviton by the number density of gravitons, you get the energy density of gravitons, which is this time-time component of the stress energy tensor. And so down here, where I argued that the number of flux vector for gravitons should look like this, the correct statement is the number of flux vector for gravitons is equal to 1 over 16 pi h bar squared times the average over a wavelength of h plus squared plus h cross squared times k mu. So that's the correct statement that comes from applying geometric optics to this Isaacson stress energy tensor. Okay. I'll give you some exercises to work with this so you feel a little more comfortable. Okay, so we should let Mark Wise have the room. Thank you.